So we have made it to chapter 10. So we're now going to start making inferences about two population means. This indicates that we are going to be looking at two different populations and comparing them. This is very, very useful when we are doing experimental design or really any kind of design because we're trying to compare two different situations to each other. So especially when we're doing experimental design, when we do a control group with a treatment group, those can be considered two different populations, or that we're trying to make an inference on what, say, a drug will do for each one of these populations or not do. So here's the basic idea and the process of doing this. So we have two populations. One of these populations may be a control group, and one may be an experimental group. So here we might have the control and an experimental group. This is just one possibility in order to do this. And then, of course, we take our sample. We create a sample of a population of volunteers that we have, what have you. We create a random sample 1 and a random sample 2, and then we get their sample mean, and then we compare these means, and we're going to make inferences about the difference in the true mu1 and mu2. Okay, so because in population 1, there's some mean here, and we want to see if the true mean is different. Of course, these are likely to be a little bit different at least, but can they indicate that the actual real means are different? And what we call that is statistical significance. And we've talked about that before, statistical significance, if they're statistically significantly different. Okay, so how do we set up a two-mean hypothesis test? Well, the first thing we have to ask ourselves is, are our assumptions met? So we have to make assumptions about this every single time. We need to make sure that they're from a simple random sample. And yes, there's other type of sampling, but remember, I've taken a whole class in sampling, and unfortunately, to do these tests, when you do a different type of sampling, there's another thing that has to be multiplied or divided or what have you to actually create accurate confidence intervals and hypothesis test. And each one has to be from a normal population or have a relatively large sample size. And again, each of them should be at least 30, or know that they come from at least approximately normal distributions. So, of course, always the next thing we do is state the null and alternative hypothesis. So the null hypothesis, just like all our other null hypotheses, is always equal. Our alternative hypothesis can be less than, so the first is less than the second, the first is more than the second, or they're simply not equal to each other. Now we have an extra step in here, and that is to decide whether or not we pool the standard deviations. So in other words, can we consider the population standard deviations to be equal? So the question is this a true statement? Is sigma 1 equal to sigma 2? Or do we have reason to believe that they're not? If we have reason to believe that these two are not equal to each other, then we cannot pool. And we'll talk about that in a little bit. If we do pool, when we perform the test, we give the pooled standard deviation. If not, we give the degrees of freedom. We'll talk about this. This is coming soon. This is the next thing to talk about. Give the test statistic, the p-value, a decision, and your conclusion. In words. Okay, moving on. Now let's talk about how these things are distributed and how we can create a test for this. So let's say we have two sample means. Right now I'm just going to call them X and Y just because they can just as easily be X1 and X2. I'm just doing that. It's easier to differentiate between them if we call them something different. And they are normally distributed due to the central limit theorem, i.e. they're a large sample or they come from a normally distributed population. Then X bar minus Y bar is also normal with mean mu of X minus the mean of Y. So this is the mean of the X's minus the mean of the Y's. Oops, I said Y's. I said X again. So the difference in their sample mean and the mean of the difference in their sample mean is the difference of the means. That makes sense. And here's their standard deviation of the difference. And the reason this has to be added instead of subtracted is because, remember, if we have two different distributions, each one of these has their own standard deviations. The standard deviation isn't going to get smaller, it's going to get bigger. Because now you've got the variability of not just X, but now you have the X bar, but now you have the variability of Y bar. So that's why we have to add them together instead of subtract them. So the standardized form of X bar minus Y bar is Z equals X bar minus Y bar minus the difference in the mu's, because remember, we have our X minus mu over sigma. And then we divide it by the standard deviation. So remember, we have the normal variable minus its mean divided by its standard deviation. That standardizes something. All right, let's move on. So what if we do not know the population standard deviations? So in other words, we don't know if we can reasonably conclude this. Is this reasonable to assume? And what we're going to do is to find out if that's reasonable to assume, we're going to look at the S squareds, because we're going to have an S1 and an S2, right? So population 1, population 2. So what's going to happen is, what we're going to do is we're going to take whichever one is bigger, the larger one, it has to be the larger one on top. We're going to square it. And then the smaller one on the bottom and square that. And we're going to call that F. So let's do some examples. So let's say that we know that S1 is 2 and S2 is 3. We find our F. Our F is equal to, in other words, so we take our larger one, which is now 3, so 9 over 4. And that is, let's see, 2 and a fourth. And then we compare it. Case 1, this is less than 3. So then we would say, okay. But if S1 equals 2 and S2 were to equal, say, 5, then our F would be 25 over 4. Remember, I have to square these. And then what is that? Let's see, 6 and a quarter, which is greater than 3. Do not pool. So this is the kind of thing that we're going to do, and that's all there is to it. And you might have to use your calculator. It might not be quite these little simple ones. So case 2, we cannot assume that sigma 1 and sigma 2 are equal. Here we can assume, even though our S's are different by 1, the ratio of them, of their variances, because remember the square of the standard deviation is called a variance, the ratio of the squares is less than 3. So we can assume that sigma 1 and sigma 2 are equal, or at least very, very close to each other. We have no reason to believe that they are not very, very similar. So, once we do that, let's look at case 1. So this is the case where the S's are close enough together to assume that the population standard deviations are equal. So if sigma x is equal to sigma y, then the standardized form, and we're just going to call it some sigma. So look here, I just took out the x and the y down here at the bottom. Well, if these are the same, these can be factored out. And then now I have the square root of x, or the square root of sigma squared. So now I can just put this sigma on the outside. So if we replace sigma with s, because remember, we don't know sigma. We don't know this. Z becomes t, and actually we're replacing this with an SP because of pooled standard deviation. Z becomes t, and remember, in a hypothesis test, we always assume that the null hypothesis is true until proven otherwise. That would make mu1 equal to mu2. So this piece right here would be 0. If mu1 equals mu2, then these go to 0. Actually, I should have said xy on this one. So t equals x bar minus y bar divided by SP times the square root of 1 over x nx plus ny. Now, a lot of times we'll actually call that, we'll use 1 and 2, so we'll actually call that x1 minus y1, or x1 minus x1 bar minus x2 bar divided by S pooled times the square root of 1 over n1 plus 1 over n2. And that's my test statistic, where my S pooled looks like this. And that looks a little bit like a mess. It's not really that hard. It's kind of a weighted average of the squared standard deviations or the variances. However, your calculator is actually going to give you this value, so it's kind of nice. Okay, so what if f is greater than or equal to 3, and we cannot assume the population standard deviations are equal? So if we cannot assume this, we say that sigma x and sigma y are completely different, or sigma 1 and sigma 2. Then we replace the sigmas with the s's. Z becomes t, and again, we can assume that the null hypothesis is true, so that the mu's, the population means, are equal. Then we have this, which is not very hard. It's fairly simple. However, the problem is, and usually again, if we write it with 1s and 2s, it's written this way. Square root of s1 squared over n1 plus the square of s2 over n2, and then the square root of the whole thing. And here's the degrees of freedom. Yeah, I know what you're thinking. I do not want to have to do that. And generally speaking, again, this is why it's nice to have our calculators. We don't have to do this by hand. I just wanted you to see what it looks like. It's kind of a mess. It is a little more difficult than the S pooled for the case 1, but like I said, and it has to be rounded down to the next lower integer in order to look it up. So, but your calculator can calculate it fairly easily, and that's what makes it kind of nice. Okay. So let's talk about how we do this, how we perform a two-mean t-test, two-SAMP t-test is what it's called, using your calculator. Now again, we have to make sure our assumptions are met. Okay. Sigma's unknown, samples are independent. Okay, so let's just say for a minute that we are given some information. And I want to go down a couple of slides and show you something first before we do this. Okay, so here's the example that I have. So let's say that we want to investigate a new fertilizer treatment for the growth of plants. So we have our nice little beautiful greenhouse, and here is our new fertilizer that we're making, and we're going to compare that to water only. So we're going to see, does this fertilizer make our plants grow better? And we measure the plants. Let's say we measure them after 1 month and see if the new fertilizer results in taller plants than water only. So let's say that after a month we get X1 bar to be the plants have an average of 12 inches with a standard deviation of 4, and we have 27 plants. You can count them if you want. And over here with the water, we've got the average height was 10 inches. The standard deviation is 3. And N2, we also have 27 of these plants. So we want to compare this. So we go, okay, now let's go to our calculator. And I'm going to go back to, whoops. Oh no. That didn't work like I wanted to, did it? Okay. Let's go back up to the instructions so you can follow along. Okay. All right. So what we're going to do is, your first thing you're going to do is write down your null and alternative. So we want to know what. Remember, the question being asked goes in the alternative. So in this case, does the data present sufficient evidence to conclude that the fertilizer is making the plants grow higher than the water only? So in other words, is the fertilizer, so the mean height of the fertilized plants, greater than the mean height of the not fertilized plants? And I don't even have to call this 1 and 2. This is what it calls it in your calculator, but I can also call this fertilizer and water if I want, just so I know that exactly what it was. And that kind of helps me sometimes keep track of what 1 and 2 is. So here's my null and alternative. I always want to write that down first. You guys know that, because I want to be able to see exactly what I'm doing. So let's go and let's look at stat. We go over to tests, and we go to number 4, which is 2 SAMPS t-test, number 4. And in this case, we're not given statistics, we're given data. You can always be given statistics in anything, or given data. You use lists, but we're given statistics. So we switch over to that and hit enter. Now we have everything we need. So X1 bar. Our X1 bar was 12. SX1 was 4. N1, 27. X2, 10. SX2, 3. And N2 is 27. And we know that we want greater than. And pooled. Uh-oh. We didn't find out whether we can pool or not. We need to use our ratio F. So let's find our F. Remember, we take the larger s squared over the smaller s squared. So in this case, our larger one is 4. So we want 4 squared over 3 squared, which is 16 over 9, which is 1 7/9, I believe. Definitely less than 3. So pool pooled equals yes. So when we go to this pooled part, we're going to go to yes. Make sure you click enter because you know it doesn't take unless you do. So then we want to calculate. And here's our information. So here is our output. On the top line, you see your alternative hypothesis. So this is right here. mu1 is equal to mu, or is greater than mu2. Is that what we wanted? Let's see. Yes, that's what we wanted. So now we look at the rest of this. So we go t. So in our case, we got a t equal to 2.078. That's good. I don't know how many place to put it here. We'll make this smaller. There we go. Now I have a place to put it. Okay. And then we have p as our p-value right here, just like usual. 0.0213. Degrees of freedom, 52. Not really anything you have to report. But remember that's 27 plus 27 minus 2. So that's correct. Oops. My test went away. And that's okay because most of you can actually get it right back. It keeps the same thing from time to time. So if you make one mistake, you can always go back and fix it. So then you see your sample means again, your sample standard deviations. And notice what it gives you. For pooled test, it gives you your S, it gives SXP. This is your S pooled. I would like to see that number reported. If for nothing else, I'm going to ask for it on the test anyway, so you might as well get used to it. And of course, it gives me my ends just to make sure that I can look at all this to make sure I didn't put any typos in. So, close that now. So now I'm going to, once I make sure everything's right, I look at my p-value and I say, okay, is my p-value less than my significance level? So I'm not really given a significance level in this problem. So let's say that it was 5%. Is this less than 5%? And the answer is yes. So I would say that we're going to reject the null, and at the 5% significance level, we have sufficient evidence to conclude that the mean growth of the fertilized plants, and I notice I use the word mean or average, is higher than the water only plants. So I put it back into words. You're basically, remember, you can conclude or you can't conclude your alternative hypothesis. My alternative was that the mean growth of the fertilized plants was higher than the mean growth of the water-only plants. All right, so now what about a confidence interval? Well, when we do a confidence interval of this sort, it is involving two means, and we're really looking at the confidence interval in the difference of the two means. Okay, so here's the difference when we can pool and when we can't. So here's what they look like when we write them out. And of course, we use T with the appropriate confidence level and N1 plus N2 minus 2. Here we use the T with the appropriate confidence level and this weird degrees of freedom that we found on the previous page. And what we're going to be doing is using 2samp T int. So what's very nice also about your calculators is that when I go to stat, if I go down to 2 samp t interval, notice everything is in there still. Everything that I just did with the test, I hate that, is still in there. So let's say we're going to do a 95% confidence level. Yes, it is pooled. And we calculate. And we get 0.0691 to 3.931. And we're going to say we are 95% confident. And here's where you have to be careful. That the difference in growth between the fertilized, nope, I forgot the word, the average or mean difference in growth between the fertilized and water only plants lies between 0.0691 inches and 3.931 inches. Now, looking at this, what can you also conclude from this number? Well, if you look at this, can you conclude the same thing that we conclude before? Can you conclude that the fertilized plants are always larger? And the answer to that is yes, we can. That mu2 is greater than mu1 because 0 is not in our interval. If 0 is not in this interval, then we just made the exact same conclusion that we made before. Because looking at that, we're 95% confident that it's above 0. Because even the lower end is above 0. So that means that we're pretty confident that the fertilizer, on average anyway, seems to be working. And so that's how you would do that. So just really quick, I want to do a quick example. Let's just say for the sake of the argument that our standard deviations were different. Now, let's just say, let's go down here to the next page. So let's just say that this one was just a lot more variable. So let's just say that this one was actually 5 instead of 4. And how does that change our answer in the problem? Okay, so what happens is if that was 5 instead of 4, then our F would now be 25 over 9, which, no, that's still less than 3. Oh, darn. Okay, fine, I'm going to make it 6. Now it's 36 over 9, which is 4, which is greater than 3. So now we cannot pool. So let's say that we cannot pool. So we go over here and we go to our test. We have to change this standard deviation now to 6. But we recognize that we have to say no when we pool. And let's calculate. I want to show you the difference. So in this case, we got a T of 1.55. We have the same mu1 greater than mu2. And notice the degrees of freedom. So we got our p-value of 0.0648. Our degrees of freedom is a weird number. That's a weird thing for degrees of freedom to be. So we would have to call that 38 degrees of freedom. So we had fewer degrees of freedom here. So that was one issue that we have. And the other issue, and the reason that in this case you'll notice that 0.06 is above 5%, we do not reject in this case because we do not have sufficient evidence to conclude that the fertilizer results in higher plant growth. And I'm writing it slightly different this time just to show that you can write it differently. On average than water only. So we do not have sufficient evidence to prove that now. Now, one of the reasons that we don't isn't so much the difference between pooling and not pooling. The biggest issue that we have is the variability of this one. Because if you think about it, if you have, these are both normal distributions. If this is normal somewhere around here, this is a lot more variable. So this would be like this. I mean, even though the thing is, it goes like that. And they cross over just way too much. Which means that they could actually simply just have a normal distribution kind of somewhere in the middle for the real distribution of either one of them and not make a difference. So that's why we couldn't prove a difference this time. So it's kind of neat. So next time we're going to do not independent samples. And that's it. Oh, one more thing. I'm sorry. Hang on. I wanted to do one more thing. I wanted to do the interval. And then I'm done, I promise. I'm just going to do the interval. It'll be short. Oops. Hey now. Okay. 2 samp tient with all the same information. Not pooled this time. What do we get? Negative 0.613 to 4.613. Now, notice that this interval contains 0. So the difference between mu1 and mu2 could be in the middle. So the difference, we are 95% confident the difference in means is between, now we have negative 0.613 and 4.613 inches. So what happens now, you have to think about it. Yes, on average, it seems like the new fertilizer is a little bit higher, maybe, but that could just be a fluke, remember? That can just be because of the plants that you had. And in fact, that's going to happen 6.5% of the time. It's just because of random chance. So when we say we're between negative and positive, that means 0 is in this interval. So it is possible that there is no difference between the new fertilizer and the water, which is kind of what we did here. We don't have enough evidence to say that there's different. So we kind of have to default that they could be the same, even if they're probably not. Now I'm actually done. I will come back with the 10.2.